Economic Geology and Mineral Resources of India. Topic: Deposits related to the Metamorphism, Part 2. Metamorphogenic ore and industrial mineral deposits. Objectives: Features of metamorphogenesis, types of metamorphogenic ore deposits, mode of formation of some industrial mineral due to metamorphogenesis. Introduction. Metamorphogenic ore deposits may be defined as those deposits which demonstrably owe their origin and existence to the process of metamorphism and attendant deformation, not merely by reconstitution, as in the case of, say, kyanite, sillimanite, wollastonite deposits, but also through creative processes of transport concentration and or emplacement. Materials for such metamorphogenic deposits could presumably come from pre-existing ore bodies of any conceivable origin, some special rock types such as sedimentary iron formation, black shales which already had above Clark concentration of some metals, and extensive volumes of virtually any sedimentary igneous or metamorphic rock containing the metals in minor or trace amounts. Perceived mechanisms have all been covered under mobilization, which incorporates any process by which the ore materials are put in a condition that enables them to move from one place to another. The term mobilization does not specify anything about the mechanism or the state or the distance of transport. Remobilization, another term, should etymologically refer to the phenomenon of reworking from pre-existing deposits or at least some pre-concentrated source rocks to generate new ore bodies. Metamorphogenic ore deposits can be classified into the following three categories with substantial overlap. A. Metamorphogenic deposits regenerated from pre-existing ore bodies involving remobilization sensu stricto. Metamorphogenic deposits derived from pre-concentrated source bed type of precursors, and metamorphogenic deposits derived from normal rock types, perhaps slightly enriched in metals. Deposits regenerated from pre-existing ore bodies. Ore geologists have repeatedly emphasized the inadequacy of metamorphic processes in transporting substantial tonnage of ores far beyond the confines of the parent ore body. However, certain sulfide deposits confined to metamorphic terrains clearly indicate their origin through the process of remobilization of ore components from pre-existing ore bodies and or mobilization from disseminations in the rock matrix. Example, Franklin Furnace and Starling Hill sulfide deposits, New York, USA. Broken Hill lead zinc deposits, New South Wales, Australia. Felbertal scheelite deposit, Austria. Among the above listed deposits, the Broken Hill base metal deposits are a clear case of regeneration of new ore bodies at distances of kilometers from pre-existing ones through chemical remobilization by hydrothermal processes accompanying regional metamorphism, especially polyphase and retrograde rehydrating metamorphism. They provide clear evidences of evolution through four major processes. A. Syn-sedimentary and or syn-volcanic base metal deposition of stratiform type. B. Strata-bound metamorphogenic type derived from the first. C. Post-metamorphic vein type. And D. Intrusive related at intrusive exocontact and or as disseminations within intrusive deposits. The Proterozoic Vidya-mitra supergroup, approximately 1,820 million years, at Broken Hill mining district is composed of metasedimentary and metavolcanics with minor anatectic intrusives that had undergone A. At least two amphibolite granulite facies metamorphic events M1 and M2, B. Three deformation events D1, D2 and D3 during high-grade metamorphism approximately 1,660 million years. C. Retrogression. Phase 1 after peak metamorphism approximately 1,605 million years. D. Felsic magmatic event approximately 1,490 million years. E. An ultrabasic intrusion episode. F. Another thermal approximately 350 degrees centigrade pulse at approximately 520 million years. and a retrogression phase 2 confined along shear zones with evidence of focused fluid flow. The total spectrum of mineralization in the terrain is bewilderingly varied, consists of 23 ore types, Bonds 1987, and has evolved through diverse processes during a time span of some 1,300 million years. Besides the huge Broken Hill main lode, more than 2,000 mineralized occurrences of diverse style and variable composition, grade and tonnage have been described. In the Broken Hill terrain, the metallogenic style stratigraphically changes from iron, copper, cobalt, uranium to lead, silver, zinc, tungsten to dominantly tin in the uppermost Sundown and Paragon groups of the Vidya-mitra supergroup. Thus, metallogenesis in the Broken Hill region began with a widespread sedimentary concentrations ranging from discrete stratiform ore bodies to sparse disseminations. High-grade metamorphism and deformation induced distinctive fabrics and reactions while partly remobilizing or mobilizing some constituents to yield mostly strata-bound, coarse-grained, transgressive ore bodies during the weaning stages. Localized generation of hydrous melts concentrating W from metavolcanics and Sn from metasediments gave rise to stratigraphically controlled W-bearing and Sn-bearing pegmatites. Retrogression 2 following the last thermal deformational episode activated the shears where the low Pt, silver, lead, siderite, quartz veins formed after cessation of retrograde deformation. The Felbertal tungsten deposit in Austria, which is one of the largest tungsten deposits in the world, underwent at least 2 metamorphic events during Varsican amphibolite facies and alpine greenschist lower amphibolite facies orogenize. 3 different generations of scheelite ore, 188 to 224 million years, 110 to 132 million years, and 40 to 55 million years, represented by fine-grained first generation, porphyroblastic second generation, and metacrysts third generation, are reported from the area. Deposits derived from pre-concentrated source bed of protoliths. Occurrence of massive iron ore bodies in banded magnetite quartzites of several Precambrian cratonic areas can be considered as an example of metamorphogenic ore derived from pre-concentrated source bed. Belivetsov 1964 drew attention to many massive hematite, magnetite ore bodies in regionally metamorphosed banded iron magnetites formation BIF in Ukraine and their similarity with those in Indian, African, Canadian and Brazilian shield areas. These huge concentrations, totally unrelated to topography and water table and confined within the BIF, are characterized by A. Analogous composition of ores and their host. B. Presence of the same suit of minor and trace elements in virtually the same proportions in the ore and in the host. C. Delicate preservation of finest textural details of the host rock by the ore. D. Location of ore bodies in flexures and gentle warps. E. Thinning out of quartzose layers and convergence of iron oxide layer towards the ore bodies. And F. Too low content of aluminum oxide and phosphorus oxide in the ore for any supergene derivation. Structurally controlled hypogene replacement of the protor beds in low pressure zones by strata confined ore bearing fluid originating during regional metamorphism has been envisaged for the genesis of the rich iron ore pockets within the BIF. Metalliferous black shale series can be considered as another example of metamorphogenic ore occurrence. It is a dark-colored mud rock chert carbonate rock rich in sulfides and organic matter, organic carbon greater than 1%. It hosts variety of mineral deposits like silver, silver gold, copper, silver vanadium, uranium, nickel molybdenum, platinum group elements, antimony, strontium, mercury, and germanium. Multiple stages of re-enrichment of such sedimentary deposits in black shale series during diagenesis and metamorphism have been visualized. Fall bands, which is considered to be metamorphosed equivalent of black shale series, contain silver, nickel, cobalt paragenesis within carbonate veins intersecting fall bands. High enrichment factor of silver and relative immobility of nickel and cobalt in black shales during metamorphism account for retention of these elements in the metamorphosed fall band. Deposits with metals derived from normal rock types by metamorphic fluids, metamorphogenic ores sensu stricto, devolatilization reactions during prograde regional metamorphism releases large volumes of metamorphic fluids. Such fluids have been looked upon as potential mineralizers if some physico-chemical and lithotectonic conditions are just right. Epithermal kaolin gold deposits at Nevada, USA, also known in literature as invisible gold deposits, owing to the occurrence of gold as very fine metallic particles. Archean greenstone belt gold deposits and turbidite-hosted slate belt gold deposits all display certain unexpected commonalities in respect of their thermal regimes and fluid composition, even though their age, host lithology, structural setting, depth of formation, and isotopic signatures are widely diverse. Phillips, 1993. First, for these deposits, a high thermal gradient is either evident, example, Archean greenstone belt, or readily inferable, example, Victorian turbidite slate belt. The ore fluid is characteristically of low solubility, with variable proportion of carbon dioxide in a water carbon dioxide plus or minus nitrogen mixture containing reduced sulfur and registering a temperature greater than 200 degrees centigrade. Fluid inclusion studies carried out on the gold ores of Yilgarn Block, Western Australia, and Timmins Goldfield in Ontario, Canada indicate that the ore fluids are characterized by low salinity, water carbon dioxide, hydrogen sulfide composition, and reduced sulfur. These ore fluids match well with the fluids of prograde metamorphism witnessed by the greenstone belts. In the kaolin type gold deposits, composition of ore fluids, moderate carbon dioxide, low to moderate salinity, and gold sulfur linkage strongly point to a likely metamorphic ancestry of the ore fluid. In the late Silurian turbidite hosted slate belt gold deposits at Hill End Goldfield, New South Wales, Australia, formation of concordant and discordant vein gold deposits was coeval with early Carboniferous deformation and metamorphism. Fluid inclusions are characterized by a. Low salinity 0.1 to 3.6 weight percentage of sodium chloride equivalent. B. Dominance of nitrogen in the earliest, highest temperature inclusions. C. Dominance of methane during main stage gold deposition and carbon dioxide in the late stage mineralization. And D. Delta O 18 values for vein quartz 15.1 to 17.1 per mil and vein carbonate 11.3 to 13.4 per mil, and suggestive of metamorphic equilibration at their respective temperatures. Lead isotope data from pyrite, arsenopyrite, galena, and gold cluster into two discrete populations which are interpreted as representing two stages of mineralization. Mesothermal gold bearing productive lodes of late tertiary age that served as source material for placer gold deposits at Alaska, USA are assigned metamorphic origin on the basis of A. Fluid chemistry and B. Rigorously constrained temporal relation between metamorphism and gold mineralization. Further, the ages of gold mineralization, approximately 57.6 to 61.7 million years, 40 AR or 39 AR of muscovite from lodes. Magmatic intrusion, approximately 70 to 72 million years, Susitna batholith, and regional metamorphism, 62 million years. Biotite, closure temperature of approximately 280 degrees centigrade, are well constrained and imply a close temporal congruence of mineralization and metamorphism. BIF hosted Archean gold deposits have been ascribed to epigenetic metamorphic fluids on the basis of fluid inclusion studies and consideration of the geochemical behavior of gold. Metamorphogenic origin upgradation for several types of uranium mineralization has been invoked on two grounds. Uranium mineralization during regional metamorphism is an established fact since high-grade metamorphic rocks, as a rule, are depleted in uranium compared to their lower-grade metamorphic equivalents. Also, syn or late metamorphic timings has been established in many instances for deposits in ultramafic rocks and in some unconformity type deposits. Uranium deposits in the Rosing district, Namibia, are associated with late tectonic anatectic granites, pegmatites, and alaskites, which are inferred to have incorporated the metal from Proterozoic uraniferous shelf sediments during syn-metamorphic partial melting when uranium strongly partitions into silicate melts. Reprecipitation from liberated fluid has taken place not very far from the locales of partial melting in presence of reductants like organic matter, graphite, or ferrous iron bearing minerals. Metamorphogenic deposits of industrial minerals. Introduction. Several kinds of industrial mineral deposits are formed as a result of regional metamorphism. The source materials are rock constituents that have undergone recrystallization or recombination or both. Rarely, water or carbon dioxide has been added, but other new constituents are not introduced. The enclosing rocks are wholly or in part metamorphosed. It is a rock metamorphism that has given rise to the deposits. The chief deposits thus formed are asbestos, graphite, talc, soapstone, andalusite, sillimanite, kyanite, garnet, and wollastonite. Graphite. Major producers of graphite are China, South Korea, Russia, Brazil, India, Mexico, Austria, North Korea, Slovakia, and Canada. Graphite occurs in two forms: amorphous, microcrystalline, and crystalline. It is graded primarily on its carbon content, and the graphite produced in China, Mexico, and South Korea contains 50 to 90% carbon. Majority of the graphite occurrences are metamorphic in origin, and only subordinate amounts are won from vein-type graphite occurrences and residual deposits. Metamorphogenic graphite results largely from the contact or regional metamorphism of organic matter in the sediments. The degree of graphitization depends principally on temperature, but pressure and the nature of the original organic matter also play a part. True graphite probably forms above 400 degrees centigrade. Metamorphosed coal seams are important graphite producers in several countries. For example, Jixi in Heilongjiang province, China, Kurai deposit of the Tunguska Basin, Russia, Mexico. At Kurai deposit, upper Paleozoic coal measures were subjected to strong contact metamorphism through the effect of Siberian traps. In Mexico, Triassic coals have been metamorphosed to mixtures of graphite, anthracite, and coke by granite intrusion. A large tonnage of metamorphic graphite comes from metamorphosed black shales and carbonaceous limestone. At Kulsuktan in Uzbekistan, a gabbroic intrusion into limestone has given rise to pyroxene, garnet, wollastonite, graphite hornfels or skarn. Graphite produced by regional metamorphism is an increasingly important source, and many mines work this type of deposit. Deposits in Granvacan zone, Austria, and calgraphite mines in Canada. In Sri Lanka, vein-type graphite deposits are located at Bagola and Kahatagaha, Kolongaha. These deposits occur in Precambrian high-grade metamorphic terrain dominated by granulite facies rocks. At Bagola mine, the immediate host rocks are quartzo-feldspathic biotite and hornblende gneiss with garnet gneiss and a few small lenses of calciferous. The graphite veins are mineralized fractures whose thickness varies from few millimeters to about 1 meter. The average ore contains over 90% carbon. The genesis of vein graphite has been much debated over the last century. In a recent study of the Bagola ore bodies, Katz 1987 suggested that carbon dioxide-rich fluids characteristics of granulite facies terrains became sufficiently focused to produce hydraulic fracturing and precipitate graphite. Asbestos. There are two main groups of asbestos minerals, serpentine and amphibole. Serpentines are hydrous magnesium silicates. chrysotile and picrolite are of the same composition as serpentine and constitute serpentine asbestos. The amphiboles are silicates of calcium, magnesium, iron, sodium and aluminium. They comprise the minerals amosite, crocidolite, tremolite, actinolite and anthophyllite. Crocidolite is banned in a number of European countries. At present, about 95% of world production of asbestos is of chrysotile. Chrysotile asbestos occurs in serpentine that has been altered from ultrabasic igneous rocks such as peridotite or dunite or magnesian limestones or dolomite. The serpentinized ultrabasic rocks account for approximately 93% of the world's asbestos supply. Chrysotile fibers, cross fiber, slip fiber and mass fiber range in size up to 10 to 12 centimeters in length. Most of them are less than 2 centimeters. It may make up from 2 to 20% of the serpentinized rock. Most valuable deposits of chrysotile asbestos are found in Transvaal, South Africa and northern British Columbia. The leading producers are Russia, Canada and Zimbabwe. Chrysotile asbestos is confined entirely to serpentine and strictly speaking is a fibrous variety of serpentine. Serpentinization is an autometamorphic process and in the ultrabasic rocks such as dunite, serpentinization has proceeded along fractures. Chrysotile is not formed except where there is serpentinization, but serpentine may occur without chrysotile. Amphibole asbestos, crocidolite, anthophyllite, amosite are inferior in quality to chrysotile. Crocidolite and amosite are found in slates, schists and banded ironstones over an extensive belt in Transvaal and Cape Province of South Africa. They occur as cross fibers in greater lengths than chrysotile. Crocidolite deposits are said to be the most extensive asbestos deposits in the world, but only make up 3.5% of the world's asbestos market. Anthophyllite occurs as mass fiber with some slip fiber. It occurs as lenses and pockets in peridotite and pyroxenite. Fibrous material may make up 90% of the rocks. The crocidolite found in banded ironstones is thought to have originated by molecular reorganization without essential transfer of materials or constituents of the enclosing banded ironstones. Deep burial is thought to have supplied heat and pressure that resulted in the metamorphism of the rock constituents into blue asbestos. The amosite is chemically dissimilar to the enclosing rocks, and its occurrence around the contact areole of the Bushveld complex suggests contributions from solutions related to Bushveld magmatic activity in addition to static metamorphism. Talc, steatite, soapstone. Talc is a hydrous magnesium silicate. Steatite is a massive compact variety of talc. Another talky rock, for example, soapstone, is a soft rock composed essentially of talc but also containing chlorite, serpentine, magnesite, antigorite and enstatite. Metamorphogenic deposits of industrial minerals. Commercial talc and soapstone deposits occur in 1. Metamorphosed ultrabasic rocks, 2. Dolomitic limestones and 3. At contact metamorphic zones adjacent to basic and ultrabasic intrusive rocks and are largely confined to Precambrian terrains. The best quality talc comes from metamorphosed dolomitic limestones and is generally associated with tremolite, actinolite and related minerals. The deposits in and associated with ultramafic mosses are more numerous but smaller than those in altered dolomitic limestones. Ultrabasic rock-hosted talc occurs with serpentine, whose formation preceded that of talc. Example, soapstone deposits of Virginia. Talc is an alteration product of original or secondary magnesian minerals of rocks. It results from mild hydrothermal metasomatism, perhaps aided by simple dynamic metamorphism. Talc is pseudomorphic after minerals like tremolite, actinolite, enstatite, diopside, olivine, serpentine, chlorite, amphibole, epidot, and mica. It may be formed from any magnesian amphibole or pyroxene when acted upon by carbon dioxide and water according to the reaction. Dolomite limestone hosted talc deposits are encountered in Ontario, New York, North Carolina, Georgia, Bavaria, and Austria. Andalusite, kyanite, and sillimanite have identical composition, aluminum oxide and silicon oxide, but differ in crystallization. Andalusite and sillimanite being orthorhombic and kyanite triclinic. At high temperatures of 1100 degrees centigrade to 1650 degrees centigrade, these minerals change over to mullite. Andalusite is stable at high temperatures and low pressures. Kyanite at medium temperatures and high pressures, and sillimanite at high temperatures and high pressures. Commercial deposits of kyanite consist of disseminated crystals or small masses in gneiss or schist. Kyanite also occurs as lenses in pegmatite dikes. It is considered to have formed from mica schists or other aluminous silicate rocks by dynamothermal metamorphism, perhaps accompanied by magmatic emanations. Kyanite occurs as commercial deposits in North Carolina, Virginia, Georgia, Florida in USA, Singhbum district and Bandara district in India. In the Bandara district, kyanite and sillimanite have been formed from chlorite, muscovite schists by gaseous and hydrothermal metamorphism resulting from granitic intrusions. Andalusite occurs in argillaceous crystalline rocks and also in pegmatites. Its common associates are tourmaline, garnet, corundum, topaz, quartz, and mica. In White Mountain Deposit, California, Andalusite occurs in irregular segregations in a quartz mass enclosed by sericite schist. The deposit was formed by a sequence of metamorphic processes during which aluminous rock, volcanic or sedimentary rock was converted to Andalusite segregations as a result of pneumatolytic action by a nearby intrusive. Andalusite occurs in Hawthorne, Nevada in USA, Transvaal, South Africa, Russia, Sweden and Korea. Sillimanite occurs as slender prisms in aluminous crystalline rocks. Sillimanite results from high temperature metamorphism. In India, large deposits of sillimanite are reported from Khasi Hills, Assam. Commercial deposits are encountered in Russia, Transvaal, South Africa, Western Australia and North Carolina in USA. Garnet. Garnet is a group name applied to about 15 different complex silicate species with generally similar characteristics but of different composition. Some of the varieties are listed in Table 1. Table 1 shows the minerals of garnet group. Among the minerals of the garnet group, almandine is generally used as an abrasive, but andradite and rhodolite are also utilized. Garnets are constituents of igneous rocks and are formed by metamorphism in schists and by contact metamorphism in calcareous rocks. They are widely distributed, but commercial deposits are few. 95% of the world's production comes from the USA. The largest mine in the world being Gore Mountain garnet deposits in New York, with smaller deposits in New Hampshire, North Carolina, and Massachusetts. Negligible amounts come from Spain, Canada, Madagascar, Sri Lanka, Czechoslovakia, and India. The garnet deposits of New York are found in anorthosite and syenite bodies. These igneous bodies intrude Greenville series of gneisses, marbles, and schists at the peak of metamorphism. The almandite garnets appear to owe their origin to metamorphic hybridization and mobilization of proper proportions of magnesium, iron, aluminium, and silica at high pressures of 5 to 6 kilobar and temperatures of 450 degrees centigrade to 700 degrees centigrade. In New Hampshire, almandite garnet constitutes 40 to 60% of the enclosing garnet schist. The garnets are thought to have been formed by granitic emanations. In North Carolina, the Sugar Loaf Mountain is a deposit of rhodolite garnet, which averages 20 to 25% of the enclosing schist. In Lennox and Addington counties of Ontario, Canada, almandite is confined to gneissic rocks. Alluvial deposits of garnets are encountered in Spain, Madagascar, Sri Lanka, India, and Czechoslovakia. Wollastonite. Wollastonite has the ideal formula calcium silicate oxide, but iron, magnesium, or manganese can substitute for small amount of calcium. This mineral is now in considerable demand as it can substitute for asbestos in some of the uses of that mineral. This is particularly true of long fiber wollastonite, which is used in fiber boards and panels. Wollastonite deposits are found in USA, South Africa, Canada, Finland, and China. The majority of, if not all, wollastonite production is from contact metamorphosed impure limestones. The principal producer in the USA is the Fox Knoll mine in the Adirondack Mountains of New York State. Here, impure Proterozoic limestone in the contact areole of an anorthosite has been metamorphosed to a wollastonite garnet hornfels. This contains bands rich in one or other mineral, and the ore averages 60% wollastonite and 40% garnet plus impurities including diopside. Emery. Emery is a natural mixture of corundum, magnetite, and some hematite and spinel. Spinel emery contains considerable spinel and corundum may be lacking. Feldspathic emery contains much plagioclase. 3 commercial grades of emery are recognized: Greek, Turkish, and American. The Grecian emery is generally the hardest and the Turkish next, but the American varieties are soft. Emery is formed mainly by contact metamorphism and occurs in irregularly shaped bodies in impure crystalline limestones, altered basic igneous rocks, chlorite, and hornblende schists. In Greece, on the islands of Naxos, emery is encountered as lenticular mass, 100 meter long and up to 50 meter wide, in crystalline limestones and formed by contact metasomatism. In Aydin, Turkey, emery occurs as irregular masses, 70 meter by 100 meter, enclosed in crystalline limestones, interfabricated with schists and gneisses. Similar deposits are found in Urals, Russia. The USA contains deposits of emery in New York, Massachusetts, and Virginia states. Near Peekskill, New York, spinel emery occurs in the basic igneous complex near mica schist inclusions. At Chester, Massachusetts, emery occurs in pockets in a band of sericite schist. In Virginia, spinel emery occurs in lenticular bodies in 1. Schist and quartzite, and 2. In granite cut by pegmatite. These were formed by high temperature replacement akin to contact metasomatism. Summary. Metamorphogenic ore deposits owe their origin and existence to the process of metamorphism and attendant deformation, not merely by reconstitution, as in the case of kyanite, sillimanite, wollastonite deposits, but through creative processes of transport, concentration, and/or emplacement. Materials for such metamorphogenic deposits could presumably come from pre-existing ore bodies of any conceivable origin, some special rock types such as the sedimentary iron formation, black shales, which already had above Clore concentration of some metals, and extensive volumes of virtually any sedimentary igneous or metamorphic rock containing the metals in minor or trace amounts. Metamorphogenic ore deposits can be classified into the following 3 categories with substantial overlap. Metamorphogenic deposits regenerated from pre-existing ore bodies involving remobilization sensu stricto, for example, Franklin, Furnace, and Starling Hills sulfide deposits, New York, USA, Broken Hill lead zinc deposits, and New South Wales, Australia, Felbertal scheelite deposit, Australia. Metamorphogenic deposits derived from pre-concentrated source bed type precursors, for example, occurrence of massive iron ore bodies in BIF in Ukraine, Indian, African, Canadian, and Brazilian shield areas. Metamorphogenic deposits derived from normal rock types, perhaps slightly enriched in metals. For example, Colin gold deposits, Nevada, USA, Silurian turbidite hosted slate belt gold deposits, Hill and Goldfield, New South Wales, Australia. Metamorphogenic deposits of industrial minerals include deposits of graphite, asbestos, talc, statite, soapstone, andalusite, kyanite, sillimanite, garnet, wollastonite, and emery. Metamorphogenic graphite results largely from the contact or regional metamorphism of organic matter in the sediments. Metamorphosed coal seams are important graphite producers in several countries. There are two main groups of asbestos minerals: serpentine, chrysotile and picrolite, and amphibole, amosite, crocodolite, tremolite, actinol, anthophyllite. About 95% of world's production of asbestos is of chrysotile. Chrysotile asbestos is confined entirely to serpentine and is derived from alteration of ultrabasic igneous rocks, for example peridotite or dunite, or magnesian limestone or dolomite. Commercial deposits of talc, steatite, and soapstones occur in metamorphosed ultrabasic rocks, dolomitic limestones, and at contact metamorphic zones adjacent to basic and ultrabasic intrusives. The best quality talc comes from metamorphosed dolomitic limestones. Talc deposits result from mild hydrothermal metasomatism, perhaps aided by simple dynamic metamorphism. Commercial deposits of kyanite are encountered in gneisses and schists. They are formed in mica schists or other aluminous silicate rocks by dynamothermal metamorphism, perhaps accompanied by magmatic emanations. Andalusite and sillimanite occurs in aluminous crystalline rocks. Garnets are formed by metamorphism in schists and by contact metamorphism in calcareous rocks. Wollastonite is encountered mainly in contact metamorphosed impure limestones. Emery is a natural mixture of corundum, magnetite and some hematite and spinel occurs in crystalline limestones and is formed mainly by contact metamorphism.